Hello everyone, my name is Meng Jiao. Today I'm going to present energy-based processes for exchangeable data. This is joint work with my colleagues from Google Brain, including Bo, Hanjun, and Dale. We're interested in modeling sets, which is a widely used type of data structure in everyday life. For instance, medical records of patient information are sets. 3D point clouds captured by radar and LiDAR on self-driving cars are sets. And even an image can be represented as a set of pixels, where each pixel encodes its XY coordinates and its RGB values. Sets have two important properties: exchangeability and varying cardinality, meaning that elements in a set can exist in any order, and the number of elements in a set could vary. One straightforward strategy for modeling sets with varying cardinality might be to use recurrent neural networks that encode instance probabilities autoregressively. The chain rule of probability permits the calculation of the joint distribution over any member of the set. However, which members of the set are encoded first matters in an RNN, so the members are not exchangeable under this modeling approach. If we were to explicitly focus on exchangeability, we can apply Diffie-Netti's theorem, which says that points in a set are conditionally independent given some latent variable theta. And we can express the likelihood of a set, p of x 1 to n, in terms of a latent variable model with the prior of some simple known distribution. But in order to train this model by maximizing the likelihood, p of x of given theta needs to be trackable. So the existing work either restricts p of x given theta to some known distributions, such as Gaussian, or uses normalizing flows, which have to be invertible. Either approach would restrict the modeling flexibility. A different kind of approach that models conditional set distributions is stochastic processes. A stochastic process consists of a potentially infinite number of random variables, indexed by t, whose finite dimensional marginals obey the same distribution. Stochastic processes have the consistency property, which says that the probability of a subset of random variables is equal to the original set with additional variables marginalized out. This allows modeling sets with varying cardinality. Random variables in a stochastic process are also exchangeable. However, stochastic processes still restrict the likelihood to some simple known distributions, such as Gaussian or student t, which limits their modeling flexibility as well. In particular, if there are multiple modes in the data, such as the toy examples shown on the left column, Gaussian processes and their variants with neural network parameterization would fail because they could only capture a single mode, whereas our proposed approach is capable of capturing the multimodality in the data. So let's look at our model. We introduce energy-based processes, abbreviated as EBPs, which are essentially stochastic processes represented as latent variable models so that they inherit the exchangeability and consistency properties of stochastic processes. To enhance modeling flexibility, we use energy-based models to parameterize p of x given theta and t. EBMs are known for their flexibility because classical exponential family distributions, such as Gaussian and student t, can be easily recovered from an EBM. More importantly, we can parameterize the energy function of an EBM using deep neural networks, which are highly flexible. In fact, Deep EBMs are so flexible such that we can actually collapse the dependency on indices Ti to obtain an unconditional version of EBPs. We call this technique the neural collapsed inference in our paper. To train EBPs, we maximize the expected log likelihood over set instances from a training set D. However, there are a couple of challenges in this maximum likelihood training approach. First, the integration over the latent variable theta is not trackable. As a workaround, we apply the standard technique from variational inference to maximize the evidence lower bound instead, and apply the reparametrization trick to sample from the variational posterior Q of theta given x. The next challenge in learning EBPs is the intractable partition function in the EBM that requires integration over all x's. To get around this, we apply the adversarial dynamics embedding technique developed for exponential family estimation to learn an adversarial dual sampler, Q of x given theta. This dual sampler is augmented with an additional kinetic variable, nu, and has a trackable entropy, h of q. To parameterize the variational posterior Q of theta given x, we feed points in the set x1 to n to an MLP that outputs the mean and standard deviation of a multivariate Gaussian. And we can sample theta from this Gaussian posterior. Next, we feed this theta to an RNN or a flow-based model, depending on the application, to obtain an initial sample proposal from Q x hat given theta. This sample is then refined by Langevin dynamics guided by the gradient of the energy function. Lastly, we input both the original set x1 to n and the generated set x hat 1 to n to an MLP to train the energy function. Note here that in order to preserve exchangeability, points in the set go through the MLP independently, and a final order invariant aggregation function, such as summation, is applied to the points to obtain the final energy. Now let's look at some applications of EBPs. First, we look at conditional image completion on MNIST and Celeb A. The first row shows the context points used for learning the variational posterior Q of theta given x, where x is a subset of randomly selected or connected pixels. In MNIST, these context points are shown in black and white, and in Celeb A, they're shown in colors. In the MNIST example, we're able to sample a variety of digits conditioned on the same context. For example, the sample 1 row and the sample 2 row oftentimes show different digits, even though they're conditioned on the same context row. In Celeb A, we see that the variance of the samples reduces as the number of context points increases. This is a property of stochastic processes in general. For example, the generated faces on the first and second columns are quite different from the rest. Next, let's look at applications of unconditional EBPs in point cloud generation. For this task, we use an RNN with 4 recurrent units in a dual sampler. The point clouds on the first row are the accumulated autoregressive outputs of each of the recurrent units. The bottom 3 figures show the energy of the real and generated point clouds. We see that the learned energy function, f of x, generally matches the empirical dataset and the generated samples. We quantitatively evaluate EBP's generative modeling ability using the standard procedure developed by prior work. Specifically, We look at the Jensen-Shannon divergence, which is computed on the marginal distribution of a set of point clouds, the minimum matching distance, and the coverage between the generated and the empirical sets of point clouds. For MMD and coverage, we evaluate on two common set distance metrics, chamfer distance and the Earth mover's distance. We see that EBPs achieve competitive performance and have especially good coverage, meaning it's capable of generating a more diverse set of samples. Next, we look at EBP's performance in unsupervised representation learning of point clouds. Following the standard procedure, we first train an EBP on all 55 classes of ShapeNet and use the trained model to extract representations on ModelNet 40. The extracted features correspond to the output of the layer prior to the aggregation operator in the energy function. We then train a linear SVM on the extracted features. The SVM's accuracy of EBPs is only 0.1% away from the state of the art. Lastly, here is the special application of EBPs in denoising noisy point clouds. We feed the perturbed point clouds as initial samples to the Langevin dynamics embedding layers and run 20 steps of Langevin dynamics guided by the gradient of EBP's energy function to denoise the point clouds. You can think of the denoising procedure as points moving in the direction that decreases the energy of the point cloud. In summary, we have presented the energy-based processes for modeling set distributions that offer great flexibility, especially in modeling multimodal distributions, while preserving the exchangeability and consistency. The unconditional EBPs unify the stochastic process and latent variable perspectives of set modeling. We also developed the neural collapsed inference for learning EBPs and achieved the state-of-the-art performance on a variety of tasks. Thank you.